Good morning, everybody. Welcome back to System Software. Can everybody see my screen? Okay, excellent. Let's see how many people have joined so far. We're a little less than half. Let's give everybody 1 minute or so, and then we can start. We have a decent amount to cover today. Yeah, the recording does reduce attendance a bit. Okay, let's begin. So let me, I wanted to go back into where we are in the course a little bit. Just to kind of step back and give ourselves a little context. So we're about in the middle of the course right now, just about. And in the beginning, as hopefully you all saw, we covered some basics of compilers. We looked at system tools, set up our project for the semester. And now we're deep into the front end of the compiler, the part that processes the language, the source language. And last week we looked at regular expressions, which were a way to describe patterns of strings in using automated, using a machine to automatically process and recognize patterns in strings. And today we're going to continue that by looking at grammars and parsing and how parsing works. And in terms of the mechanics of the course, today there's the assignment due for regular expressions in finite state automata. And there's going to be a new assignment this week, due next week, next Friday, another written assignment covering the content from today's class. But also keep in mind that there is, next week, there's also due the first part of the project. I didn't quite get the schedule ideal. I didn't really want to have two things due on one day, but I also wanted to give plenty of time for the parsing project, which I think you had like 3 weeks to do. So just be aware of that next week there's this written homework from today due, and also the first part of the project due today. And of course, today is the regular expression homework due. So somebody's asking about question 1 on Piazza. Okay. So if you, this is like, your math teacher always said, show your work. If you write down your assumptions that you are making, for homework at least, we're grading for both effort and correctness. And one of the reasons that makes, so the question was in Piazza was about, what was it? Oh yeah, question 1, which is the following is true about regular languages. I added some material here, which we haven't really covered yet. And so yeah, it's kind of a logical deduction question. You know, can you find the one answer? So this says which one of the following is true about regular languages. So I was trying to imply that there's only one of these that is true. So if you figure out which one is the true one, then you can rule out all the other ones. And even though we're only covering parsers today, I was hoping you could kind of guess what the answer to that might be, because we haven't covered it yet, and one of the other ones is probably the right one. For question 5, somebody asked, do we need a table? Doing the conversion, I was hoping that you would use the subset construction to do it in the systematic way. You can certainly do it by hand, by kind of trial and error. But I just wanted you to practice that subset construction. Just do it, once or twice in your life, so you work through the algorithm. Actually, in general, the algorithms that we go through, I think it's good to go through by hand the steps of the algorithm, because remember, when you're writing algorithms, you're making a computer do that. So it's good to be able to understand in detail all the nuances of the algorithm. So you don't strictly need to have a table. I didn't ask for it, but if you're going to do the subset construction, it would be easy to show that. Yeah, so somebody mentioned that I think the table made it easier. I mean, this is the whole point of computing, is to make an explicit algorithm where you don't really have to think anymore when you're following the algorithm. You just follow the steps of it, and that gives you the answer without having to put some extra thought into the process of doing it. Instead, in computing, we put the thought into the process of making the algorithm, and the algorithm automates the processing for us. So somebody mentioned they have no epsilons in your non-deterministic finite automaton. If you use the scheme that we covered in class, those templates for each expression, each operation in the regular expression language, you would have epsilons in your non-deterministic finite automaton. But there are, of course, I mean, the DFA has no epsilons in it, and the DFA is an NFA. So there's certainly an NFA that has no epsilons for any regular expression. So again, for number 5, I didn't strictly ask for it, so I'm not going to take off points, because that doesn't say here that you should use it. But I was hoping that you would use the process we went over in class and in the Dragon book, the systematic process for doing it. I think it's a good, for computer science in general, it's good to do this rather than using your own sort of thought and cleverness to solve a single problem. Instead, apply that to making an algorithm that can automatically solve that systematically. And that's really good for the laziness virtue of programming, because why solve a problem once when you can have something that'll solve it over and over and over repeatedly without having to do that thought again. You just do the hard thinking once for the automation, and then that automation will do it for you. And this is always a problem in math for me as well, is that notation, the notation itself is not the thing it represents. There's many ways to have notation for what the subsets are, for how you draw the table. I tried to show the one that is, I think in the Dragon book, I have to look. Yeah, I think I tried to show the one that's in the Dragon book, basically, as a kind of standard, academic standard. So other questions about the homework due today, the finite automata homework? And if you haven't looked at Piazza yet, several people did ask questions there. So go there and you can look for common questions that might help you. Yeah, I mean, I wouldn't worry too much about notation and formatting. It's really the concept of each DFA state corresponds to some subset of the states in the NFA. And however you can, whatever makes sense to you in drawing that in a table, that's fine, as long as the underlying concept is there. Okay, I also wanted to go over the project one a little bit, because I think there's a bunch of stuff that is kind of left, that I left a little bit sort of intentionally vague. So the problem is the whole point of having this rigorously defined and explicitly defined parser is that there's no more ambiguity in the syntax and eventually no ambiguity in the meaning of the language, because we're specifying it in a compiler. We're specifying it in an automated way in the compiler. But that means that I made a little bit of a disconnect between the abstract syntax tree and the grammar, and was hoping that you would sort of figure out what that connection between the two is. And there are several hints to doing that. Yes, the AST is generated from the Bison grammar that you guys fill out. So if we take a look at this, go to so just to kind of review parsing a little bit, and I know we didn't really even cover parsing algorithms yet until today, but hopefully through the toy compiler you can intuitively understand that each one of these rules here is telling you basically the tree structure. It's a schema for all possible trees that any simple C programs can be represented by. So for instance, if we've got a unary expression, and a unary expression can consist of a type inside of parentheses followed by another expression. I didn't formally specify what this means, but this is a subset of C. So you can, hopefully through your knowledge of C, you can reason that, well, this is a cast expression. So the right abstract syntax tree node to represent this, and that we should construct for this construct, is a cast expression AST node. I know that wasn't made explicit or made super obvious here, but the idea is to take the names of the language constructs as represented in the abstract syntax tree and use this grammar, these semantic actions on the grammar rules to insert code to construct those abstract syntax tree nodes. Now, yeah, and so if I was to give you, I mean, the way I know how to give you a formal specification of that is basically just filling out this grammar. The grammar is the specification of how the concrete syntax, as described by the grammar, constructs the abstract syntax, the AST nodes. But there are some other hints that you can use to guide where, if you're uncertain about which AST nodes correspond to which of these grammar constructs. I noticed that, I think maybe I didn't advertise it well, but a lot of people may have missed this test cases repo. So Josh spent a lot of time making a ton of test cases that show you both the input, the simple C input, and also the expected abstract syntax tree output. So for a program like this, it gives you exactly what the abstract syntax tree is. And its format is understandably a little bit difficult to look through, but each indentation shows the children of the previous line's node. And so you can use this if you're uncertain about, well, if I have a declaration, what AST node should be created for that. This AST output uses the same names as the create functions for this. So another thing that this one's a little bit trickier, but somebody asked about hex constant. What type of number value does a hex constant use? So hex constant is also just an integer. And I didn't make this ultra explicit, but if you take a look at, say, your options for an expression, then there's no particular entry for hex here. So yeah, the only possible representation for a hex constant would be just another kind of integer. So this is a machine integer versus the integer representation in ASCII code. But that one's not obvious. It's just an integer, and character is just character expression. So somebody asked, how do you use the test cases? The same way that you use it's the same way that you run the compiler. So you run the compiler using just by building it and running the simple C program, and use cat to pass in the input file, and then you'll get the output file in via standard out. So let me show an example of this. So here's my example program. I run cat to run it, and so remember, this is piping. This is a pipe. This takes the output of the previous command cat and pipes it to the input of the next program after the pipe symbol. So whatever the output of cat is going to be passed as the input to the simple C program. And so voila, we have the output of simple C program, which is this AST printing. So other questions on project one. So it's really a little bit of a puzzle to figure out, well, so as somebody's asking, do we need to run GCC? So can anyone answer this question for your classmate? Yeah, so make does this for us. So notice when I ran make, the compiler is run for us. So CC is basically a symbolic link to GCC. And so also remember, we have to wrap our heads around this notion that we're compiling a compiler. And so the compiler itself is a program that's written in some source code, these days, usually in some source code. And in order to be able to run that compiler, we need another compiler to be able to turn that into machine code so that we can then compile other programs. But yeah, check out the first third of this class, the first few lectures, to review some of, what is compiler. Yeah, so somebody's asking, there was a good question on Piazza. People were building and running the template code and then getting some message in the output about, well, there's some null pointer error, some seg fault. I mean, it was caught. It was an error message saying that, but that's just because the parser's not done yet. So it's trying to print the AST, but the AST is not completed yet. So yes, as you start implementing these to-dos, the output will change. And one thing that I talked about in the beginning of the class is I really want to instill in this notion of how do you make an implementation correct according to specification. And it's so there are lots of ways to try to do this. And I think it's particularly for beginning programmers, it's common to just write some code and then run one input or run whatever input is given to you, and then just try to get that to work, and then just submit the exercise. But remember, the program takes many, many inputs. There's lots and lots of branching in the program. So just having one test case that's given to you is not enough to make sure that your program is right. So one really critical skill for good software engineers is being able to write test cases. There's even software engineering philosophies that revolve around just like building test cases first. That's not always there's many other philosophies about software engineering, but certainly any software engineer should be able to, as they're writing code or look at code, be able to write a test case that exercises that code. And I realize that in this grammar, it's a little bit more obscured from you, the actual C code that's being generated. But the same philosophy applies. If you're implementing some of these to-dos that covers, say, an expression that maps to an identifier, then look for make test cases or look for test cases here that also use a primary identifier. So this AST output, well, so it's a little bit obscured because you have to know what an identifier is. You know, an identifier are these strings of characters that start with a letter and have 0 or more letters or digits following it. But look to see what happens in the AST to that. Where's my grammar? So look in the AST to see what happens when you have that in your input. So for instance, from the code that I've given you, let's see if there's an int constant here. Let me find one with an integer. What else did I give you here? Create statement list, primitive type. Well, so for instance, for primitive type, you can see the AST node that gets created here in the output. And it's a little bit of like puzzle solving to try to map the possible constructs in simple C to what their AST nodes are going to look like. And I understand that this might be, so, you know, feel free to ask me or ask on Piazza for clarification about which simple C constructs correspond to which AST nodes. But the whole kind of puzzle here is taking a look at these grammar rules, figuring out which part of the simple C language they correspond to. So for instance, an if statement corresponds to, you know, an if keyword followed by parentheses and an expression, and then picking the right AST create function that represents that if statement. So some of them are clear by the name, are a good hint is the name for some of these. So for an if statement, there's something called, you know, if stmt. And if you're in doubt, then make simple C programs, run it through, or make look at these test cases that we've given you, and look for the construct that you're trying to implement, or write one yourself, and pass it to your parser. Also, don't forget that you can put printf statements here, so you can do your kind of poor man's tracing and debugging by putting printf statements to confirm whether this part of the grammar is being hit or not. Yeah, all the to-dos, they're going to follow the same pattern of setting the double money signs, which is setting the semantic value. So another way to look at it is these are each, just like in the toy compiler, we had this recursive parser. Each one of these grammar rules is like a parsing function. So there's a parsing function called primary expression. The double percent sign is like it's calling return, is setting the return value. And when you say money sign 1, 2, and 3, that's like calling the children's recursive functions in order to get their return values. So you can take a look at the toy compiler again to kind of understand intuitively how this Bison and semantic actions works. And yeah, you should take a look at the ast.h to figure out the interface to the AST. Oh, one other thing that I wanted to point out is the way lists work. So all the lists, so like expression lists, the end of the list is just like in classic linked lists in C, the end of the list is identified with a null. So, I mean, yeah, that's, you know, the standard way that linked lists are done in C. So if you look at something like statement list, which I've given you, if you've got an empty string that's matched by this statement list, then its semantic value is going to be null because it's something that represents the end of the list. And then to create a node in the list, the way this is structured is we have some element of the list followed by basically a recursive call to the statement, another statement list, the tail of the list. And so this is the pattern. This is what the semantic action looks like for creating lists from the grammar. And so this pattern you can follow for any lists in the language. I think that's why I gave this to you like this. But if you've got, say, if you've got a list where it's not empty, then this is not going to be null. Instead, this is going to be a new node where the tail is null. So whatever, yeah. Does that make sense? Any questions on that? It's just a new node where the tail is null, just like in a regular linked list. Yeah, so somebody's asking, and somebody asked this before. This is actually an interesting question about that will make syntax hopefully a little clearer. So somebody's asking about the minus symbol. That is, well, really in ASCII, it's a hyphen. And so there's a hyphen here inside of the unary operator rule, but there's also one by the binary operator. So just like in English, the word plus, for instance, might have different meanings in different situations. So it might be a verb in some situations. Well, no, is that right? 1 plus 2, is that a verb? I guess that's a verb. Or it might be a noun in some situations. So even though it's the same word, it can play a different role syntactically, and that different role syntactically maps to a different semantic meaning. So in the same way, the hyphen can mean unary minus, which means take the negative of that number, but it can also mean subtraction. And those are semantically two different things. They just happen to use the same symbol. And we can unambiguously tell the difference because they only appear in certain ways, certain orders in our input language. And this is exactly what the grammar represents. The grammar represents the legal orderings of words in the language. But more than that, those legal orderings map onto different meanings. So there's tons and tons of words that are both nouns and verbs, for instance. And their position in the sentence is actually is, if you believe that language is processed in the brain using something like grammar, then the way we actually distinguish that is because we just the way a parser does, we actually kind of infer the syntactic structure from the language itself. There's these implicit rules that aren't spoken in the language, but because we understand the rules, when we process the language, we can infer that structure just from hearing the utterance in the language. And that's actually what we're going to cover today is some of the theory behind that and the algorithms that we can use to do that kind of parsing in a machine automatically in a way that maybe we are actually doing similarly in our brains. Perhaps, although that's still, I don't think, proven yet, but there's some interesting evidence for that. Okay, other questions on the project? I think this is a good segue to the course. Okay. So today's lecture notes. Oh, I'm sorry. Yeah, somebody had a question. So somebody was confused why identifier appears twice. So this is the same reason that identifier appears many times. Identifier appears many times, but just like in C, you can have an identifier used in a declaration. You can have an identifier used to mean a variable. You can have identifier used to mean a function call. So all those are represented in the different grammar constructs. So even though it's the same kind of word, an identifier in this case, depending on where it's used, you have a different language construct. So if the identifier is just alone, then when we implement this language, that's just like in C, that's going to be a variable access, either in a variable assignment or reading that variable's value. If it's an identifier followed by a parenthesized comma delimited list of other expressions, then that's not a variable access, but that's a function call. So this is actually a very similar question to the hyphen. So even though there are many words, even though the words may be used in different ways, it's the same word, and there's nothing from the utterance in the language that tells you that, oh, this is a function call versus this is a variable access. It's the arrangement of words that tells you that information. And this actually segues perfectly into this case class. So I in order to have more time to get into this front end stuff without delaying the project, I gave you the project before we even talked about parsing. I was hoping the toy compiler would make that more intuitive, because I had to kind of organize. Yeah, it was just a way to organize the class so that we could get into the project early, so we could get to the really interesting language construct implementation without me having to go into the formal theory first. So that's what that you might be feeling, that a little bit of confusion there and vagary there. So that's why I did it in a more kind of example-driven, intuitive way. But today, hopefully, we'll sort of pull the curtain back and you'll see some of the theory behind why parsers and grammars work the way they do. So let's get into it. So today we're going to be, let's just go right into it. Okay, so we looked at regular expressions last week, and we see how they can, it's almost like magic technology. We can have this basically finite set of, or this finite representation of a pattern using a regular expression, but we can still match an infinite set of possibilities. Because of that clean star, we have all of this flexibility in the kinds of patterns that we can match. And that's actually kind of amazing, right? We have this arbitrarily long set of strings, and we can actually describe them with just some finite regular expression, finite representation. But it turns out that there are actually some limitations to regular expressions. And so this is captured quite sarcastically in this Stack Overflow post. So if anybody's done like some web UI hacking or ever had to deal with HTML, you may have come across this. You may have, or done web scraping, for instance. So this is a common thing, if you want to scrape websites or automatically download stuff, which is quasi-legal, but then you've probably encountered, well, how can I pull out information from an HTML file? Say it's just a data table. You want to collect that information from a data table and put it in a database, or figure out whether, as I'm going to plug one of my research students' apps here. He wrote an app to figure out whether public subs are on sale or not. So he wanted to scrape a web page to do it. So you can download his app; it's free. But yeah, he encountered this issue as well. How do I take an HTML file and pull out just the information that I want? So I'll plug him, Julian Braha. He's one of my research students. You can, yeah. So chicken tender subs are on sale. So that's actually the name of the app. And so there are like, apparently we're just a deluge of questions about, I'm trying to use regular expressions because many programmers know regular expressions really well, and they know it as a way to do automatic pattern matching. And there are just tons and tons of questions on Stack Overflow about trying to match patterns in HTML. And there's this incredibly sarcastic, now locked response about why you can't use regular expressions to parse HTML. And it goes into this, anyway, you can read it. It's funny for nerds. It's funny. But the main crux of why regular expressions can't parse, to see why that is, let's take a look at matching curly braces. So we all know in C the meaning of curly braces. I think it creates this nested scope. If you define variables or declare variables in between nested braces, you can't use them outside of them. If you have an if statement, the stuff inside the curly braces is only run if that if statement is true. Otherwise, the else branches run. So they're a way to kind of group statements together in a programming language. This is the crux of structured programming. I think all of you have programmed in assembly by now. In assembly, you don't have that kind of structure available to you. The only way to make that kind of separation of code is to use gotos and to just have spaghetti code, jump around to do this. And these curly braces allow you to, or in C, the curly braces allow you to group this structure in a kind of visual or really in a linguistic way. So it turns out that if we try to say, take a language where, a simple language where we just say, well, for every curly brace, for every open curly brace, have a matching closed curly brace. So, you know, as I think you all know from math notation and from programming languages, this is like, you know, first in, first out. The last curly brace matches, open curly brace matches the first closed curly brace, and so on. So you have these nested groups of stuff in your input programming language. So everyone's clear on this, right? I mean, I think you've all programmed in C, even if you weren't aware of it. You were, yeah. So somebody was already saying grammar is kind of stack-like. So this is really getting ahead to where this is going. But let me first ask you. I've already told you that regular expressions can't do this, but can we try to write a regular expression? What would a regular expression look like to match this? So can we write in some limited way, can we have something that sort of matches it in regular expressions? Any takers on trying to use regular expressions? Okay, naive attempt. Okay, this is okay. So we have a nice attempt here. Let me switch to my whiteboard here. So the attempt was, whoa, okay. So we got some interesting attempts here. So you can all see that in the chat. But let me write down some of these. So these are all interesting here. So we have match anything. Well, let me take the anythings out of here and just put the curly braces, because we only really need to think about the curly braces. So the parentheses are just part of the regular expression language. These are my terrible curly braces. So this is saying match any number of open brace followed by closed brace. So in this language, is this matched by that language? So we have open brace, closed brace, and then clean star. So it's not matched by it, right? So this only matches basically one level of nesting. So that's a good attempt. Matching one level. So we've got, this is an interesting one. So we've got closed brace or open or closed brace and any number of them. So does our input match here? This is a tricky one. It can, yes. So the first instinct is like, no, it doesn't match because I told you. Yeah, but it doesn't. It doesn't have to match. I think what you mean by that is that if we have an input program like this also matches. Yeah, and any number of curly braces. So it doesn't really capture this nesting or this grouping. So if we wanted to say no, how deeply nested these statements were, or on a programming language, we only wanted to run those statements if if the if condition is true, this regular expression wouldn't be able to capture that information that we need. Let's see, what other attempts do we have here? So this is a clever one that somebody put. Well, let me just put 3 curly braces, open curly braces followed by 3 closed curly braces. So kind of a obvious question. Does this match this utterance in the language? Yeah, it does. It does match it. But we have a similar problem where if we have, say, this utterance, this input program, it's not matched by it. So again, we're not capturing this nested structure of the language. And to kind of quickly see why this is, why these finite state machines can't capture at least an arbitrary amount of this nesting, let's try to see what a state machine that matches looks like. Yeah, so somebody said they can't count. This is the title of my next slide, but I don't actually understand, I completely understand what this means, but I always hear this said with finite state machines. But here's what this looks like in terms of a state machine. So if we've got our starting state and we match a curly brace, we want to capture the fact that the end state, that we go into some state where we match that end curly brace. And so all these other attempts where we say, well, match any number of open braces with any number of end braces doesn't capture a state that says, now we're nested one level deep. But we can make that explicit in our finite state machine. So I can say that state two here means we're one level deep in our nesting. What that means is if I have another open brace, I need to have another corresponding closed brace that I have to reach my end state. And so the problem is this works fine if we have, say, a fixed nesting level. So if we know that we're going to be only going 3 levels deep, then all we have to do is draw this connection here to say, well, up to 3, then we can start matching end curly braces. And of course, we need to draw epsilon state. Well, I shouldn't say of course, but we need to draw epsilon states, epsilon transitions to cover every possible case where we don't have more nesting going on. So does this kind of make sense for matching 3 nested curly braces? Does everyone kind of see why this works for matching start and end curly braces? Any questions on that? The problem comes when we want to have an arbitrary nesting depth. And as you can see, we just need to keep adding states to this machine. We use epsilons to either continue matching nested curly braces or to basically we want to see, okay, are we seeing another open curly brace or have we started seeing end curly braces? That's what the epsilon transition does. But yeah, so it's not, yeah. And so this actually goes beyond efficiency. So somebody said regexes don't do this efficiently. This goes beyond efficiency because a finite state machine by definition has a finite number of states. That's what makes it so, that's what makes that finiteness is what actually allows us to do, say, the subset construction algorithm works because we have a finite number of states. If there's an infinite number of states, the number of states in the DFA is also going to be infinite. Once we get into an infinite number of states, we're not a finite state machine anymore. And if the consequence of that is that we're for implementing that in physical hardware, well, just having a finite infinite amount of hardware in order to handle our input language is not really tenable. And of course, machines don't have infinite RAM either. But the point here is that finite state machines require a finite amount of state. And so if we want to allow arbitrary nesting depth and capture this hierarchical information, a finite state machine is not going to work. And the kind of, okay, does that kind of make sense? Yes, so somebody already pointed this out. So those of you who took big discrete, a push down automata can handle this. So basically if we keep track of this nesting state separately, well, yeah, we might as well cover this now. I don't have to make this a mystery novel. So the point is, instead of capturing this in the states of the machine, we can maintain a separate stack that keeps track of our nesting depth. So whenever we see a curly brace, we can basically push our nesting depth onto the stack and use that to keep track of how deeply nested we are. And then for the rest of the language, we can just use finite state machines. So okay, so this is getting a little theoretical. Let's get into this. All right, so the kind of glib way of saying this is finite automata can't count. I don't exactly know what this means, but I guess the idea is they can't count this nesting depth, or they can't understand languages where there's a, so one way to write this language in like the formal way of writing language in set notation is to say, well, this is going to be ugly because set notation usually use curly braces. But one way to describe this language is that we have n open braces followed by n close braces. And the fact that the state machine needs to count the number of open braces is something that is a type of language that the finite state machine can't handle without having an arbitrary number of states. So basically n is unbounded. And so even though machines technically don't have an infinite amount of state, we can capture this arbitrary behavior in just a stack or in RAM in the case of a physical machine. And so somebody was actually asking before, well, if regular expressions can't capture this, can't we just add stuff to the regular language, to the regular expression language? Well, then, then it wouldn't be regular expressions. Yeah, we can add stuff to it. And that's actually what we're going to do today. That's what grammars do. Questions on this so far? In big discrete, you'll go into the theory behind this. You'll learn like the pumping lemma for, I'm bringing out big words without remembering what they are. I think pumping lemma can only disprove, but not prove that it's regular or something like that. I can't remember which way it goes. Yeah, I think it can disprove it, but can't prove it. And this is like, this language is like the classic, matching parentheses is like the classic case of what a regular expression, a kind of language that a regular expression can handle. So I didn't cover, proofs. We're not going to do proofs in this class, but do it once. It gives you a good rigorous way to look at these problems. Math is actually useful for programming. As I mentioned at the beginning of the class, having some computing theory is useful, but the main point is to get the intuition behind it, why it works. It's sort of hard to recover that from all the terse syntax, terse notation that math uses. But the underlying concepts is what's important to get. Yeah, exactly. So somebody said the main takeaway is that regex can't account for matching curly braces yet. It can't account for, from a programming language perspective, we can't match parentheses. And to bring this back to this sarcastic answer, this is exactly why HTML, if you've ever looked at HTML, can't be parsed with regular expressions, because HTML is defined to have this nested structure. You can have a paragraph, and in that paragraph, you can have a div, and inside of that div, you can have a paragraph, and in that paragraph, you can have a span. And so this nested structure is in the design of HTML. Oh, okay, so some people who have done HTML, this makes sense. So it's the same thing. You're matching the start tag with the end tag, and this matching is something that regular expressions can't do. Can't do for an arbitrary amount of nesting depth. So you can always write this also is a bit kind of practical. You could write every possible nesting matching in a finite state machine if you know that you're only nesting up to like 100 levels deep. But then you're going to have to account for the fact that underneath my paragraph, I can have either a span, I can have two spans. The finite state machine just explodes in the number of states. So in that sense, it is also a case of efficiency as well. Even though physical machines are technically finite state because of finite RAM, the representation is just explodes. Right, they can't, so they can't match finite prefix. They can't match arbitrary prefix substance. I'm not sure, I don't think I understand the question actually. Somebody asking, they can't match finite prefix suffix, just everything in it. Well, so keep in mind that everything in it can also be another set of nested tags. Yeah, you can have as many open tags as you want. You can't track how deeply nested they are. And for HTML, you need that in order to represent the HTML properly. You need to understand what's nested within what. So, okay, so this is all revolving around this same idea that languages, including human languages, have this hierarchical behavior, have this kind of nested structure to them, this hierarchical syntax. So syntax informally is just the valid arrangements of words in a language. So in natural language, we see this kind of hierarchy in natural language for any speaker, even if a speaker has never learned formal language theory, or they've never taken grammar, or they've never had to study the language. Humans do seem to do this naturally. I think even as controversial as the cognitive science view of linguistics might be, nobody disputes that there is this nested structure to language. There is a question about how it's actually processed in the mind, but we can see this nested structure in these two English language examples. So take this sentence: the person walks home. In grammar school, we learn this as a sentence that has subject, verb, object. In this case, indirect object, I guess. And if we look at the second sentence, the person I went to school with walks home. So no, in any language, this isn't specific to English or any particular language. It seems to be this universal nature of human languages that when we hear this sentence, we don't. So in the first sentence, we have no problem associating the walks verb with person. We know, we can imagine, we can describe. When we describe this setting, we know it's the person that is doing the walking, and we know that's what another person means when they say it. In the second sentence, there's no confusion about the fact that with is right before walks, right? I mean, this is almost like too obvious because we all do this without even thinking about it. But if you look from a machine trying to write an algorithm that's processing this language, you might have some simple rule that says, well, okay, the verb comes after the subject. But in this case, the thing right before the verb is the word with. And no person has this confusion where they think, well, oh, it's with that's doing the walking. I mean, this doesn't even make sense to us, right? The reason for that is, in some sense, when we hear or say this sentence, when we mention the person, we almost kind of freeze the sentence for a second and then go on to describe this person using another sentence, actually. And then we kind of pop the stack and start processing the sentence that we put on freeze for a second. So this is exactly what one of your classmates mentioned before, that this is very stack-like, where there's this, just like in a function call, we freeze the processing of that function, go off and do something else, come back, pop the stack, and then continue where we left off. This is exactly what functions do in the programming language when we have a function. Does this kind of make sense? So this I went to school with is like almost like a nested structure inside of this sentence. And it's this hierarchical structure that we capture with grammars. So I think we already kind of got to this. Yeah, so hopefully this is making recursion make more sense. So as I mentioned in the beginning, this is really going to connect data structures, recursion, and language together. Yeah, so somebody's asking if the sentence is too long, our mental stack is full. I mean, there's all sorts of reasons for this. Yeah, we do have probably limited working memory. It might be easier to look at it on paper. There also might be ambiguity. So, if you've ever had a writing teacher say, well, you have a, what's it called? Where you use a pronoun, but it's not clear which part of the sentence the pronoun corresponds to. There's all sorts of ambiguous sentences. That is, sentences where you, there's some really funny classic examples of this. Something about, there's some very funny ones, like about a man eating a dog or something. Or like, I want to have you over for dinner. It could mean, this is a macabre one, but it could mean I want to eat you for dinner, or it could mean I want to invite you over for dinner. Yeah, I'm having a friend for dinner. Yeah, exactly. So this isn't really, I guess this isn't really syntactic ambiguity. This is semantic ambiguity. But there are cases where there's syntactic ambiguity. Well, I didn't prepare them. I forgot to prepare these. But yeah, anyway. So the way so somebody mentioned with a good idea, which is, can we just extend the regular expression language to account for this nested structure? So rather than extend regular expressions, perhaps surprisingly, were actually developed in the meta mathematics world, whereas the language view was developed in linguistics, very earliest largely by Chomsky. Noam Chomsky was famous for his work in linguistics and making it computational, and also later lots of others working on this as well. And there were kind of these two paths in like linguistics, seeing the computational aspect of language in linguistics, and then in metamathematics, noticing the linguistic aspects of these computational processes like finite state machines. And so in the linguistics world, Chomsky developed these notions of grammars and these hierarchies of language. Of course, grammars were not invented by Chomsky. Grammars go back thousands of years to the first recorded description of, I think, Sanskrit for the grammar of Sanskrit in this kind of hierarchical description. And so a grammar, like a regular expression, is a way to describe all possible sentences in the language. So this is, again, trying to wrap our heads around the meta language for describing a language versus the language itself. So just like in compilers, there's always this confusion that's easy to make between the meta language that's describing the language itself versus the language utterances themselves. And so we'll say this a little more. I'll try to be very clear about the notation of grammars to avoid this kind of confusion. So yeah, grammars are a way to describe this hierarchical syntax in languages that, say, have matched parentheses or nested structure. And a grammar, like a regular expression, a grammar is a scheme for describing such languages. Just like regular expressions has some special operations that allow us to describe infinite patterns that have an infinite set of possibilities, grammars allow us to also do this kind of description of an infinite set of possible input strings while being able to capture this nested structure in the language. Okay, and the way this works, the kind of key to this is to draw this distinction between the actual symbols of the language, the utterances that we hear, like where is it? Like the person walks home, the person I went to school with. All these are the words of the language. And those are symbols that are represented in the grammar. But there are special symbols in the grammar that represent the language constructs themselves. So this is a little bit of a heady idea, but let's see some examples of this. Okay, so somebody's asking, but grammars only describe all possible sentences that we make the structure for. Yeah, exactly. So we have to, just like in regular expressions, we want to describe what the language is. But if you think about it, if you want to think in a kind of physical sense, what does it mean for there to be a language without a physical representation of that language? So can English exist without some physical thing to process that language? So you can say, oh, there's this construct in English, but there's no possible way to physically describe it. Well, body language is still a language. It just has different symbols that represent. You think about it. You may think spoken English and written English are the same, but if you're going to compare it to, say, body language, well, what is ink on a piece of paper? That is nothing like the sounds that we hear with our ears. That's nothing like that. The actual utterances are different in their form, but we consider the language the same, even though actually there may be different levels of formality or different levels of tone. And actually, in spoken language, there are other sounds and aspects of the sound that we can use to convey information, like prosody, I think it's called, the kind of accent and emphasis you put on the sentence. That's something that's hard to capture in text. Although people who use texting, like on social media, they have all sorts of ways to include that kind of other emphasis that we don't have with the actual words of our language, the phonemes of our language. All right, I'm getting off on a little bit of a tangent here, but the point is, we have the symbols of the actual utterances in the language, like the words in the language. They may be represented in text. They may be represented with phonemes that are spoken. They may be done with body language or sign language, for instance. So sign language can express exactly everything that a spoken language can express and can have all this rich nested structure. but without using spoken words, just using what is effectively body language. Hand symbols are also body language. And so that part is actually not really relevant to the structure of the language. You can kind of abstract that away. And in the compiler, that's what the lexer does. The lexer just says, whatever the input, the literal input format is, I'm just going to turn that into these tokens. And the tokens are and we can describe the structure of the language in terms of those tokens, irrespective of how those tokens are actually created when we utter the language or when we read the language. I don't know, does that kind of make sense? And so we can abstract this away into symbols that represent those utterances and symbols that represent the grammar constructs themselves. So we have these kind of two types of symbols. So let's look at an example of some very simple subset of the grammar. And so as somebody pointed out, if you want to actually describe a language this way, you would need to account for all possible structures. So these grammars can be enormous. I mean, this is at least in part of the reason why, for say, machine processing of human language is done using statistical and machine learning approaches, where they may have some amount of grammar involved. They may just do pure statistical reasoning and not even think about grammar, try to kind of recover it statistically, because sitting down and describing an entire complete English grammar would be a pretty difficult task. But for programming languages, they're small enough right now, we can do this. And we also want to have that kind of, it's nice to have that kind of determinism that we get from describing the language with the grammar. Okay, so let's look at an example of a grammar. So as I mentioned, we have symbols that represent the words in the language. Like I put these in quotes in this case. So there's many ways to represent this. We're unfortunately going to see multiple ways to do this depending on, so Bison has its own way. The formal stuff, the Dragon Book has its own way. But in this example here, stuff that's quoted, by that I mean those are the actual utterances in the language. And the stuff that's not quoted, well, these are symbols that represent the grammar constructs, the language constructs. And the arrow represents a rule that says what a sentence is composed with or is comprised of, or what a sentence can be broken down into. So this is just like sentence diagramming that some people learn in grammar school. And notice here that there's only like four actual words in this grammar: the, person, store, and walks to. So this is really a verb phrase, but I just turn this, I can design the grammar however I want. So yes, some people are already constructing sentences that are valid syntactically from this. The store walks to the person. So there might be a meaning to that. I mean, there is kind of a figurative meaning to that, like online stores come to you. But this gets to this notion of this colorless green ideas sleep furiously notion that Chomsky used to illustrate this difference between syntax and semantics, that there is this notion of syntax that we seem to be able to process independently of the meaning of the sentence. We can sense this without even having to understand the meaning of the sentence. And so notice here that the language construct symbols of the language, at least in this grammar, far outstripped the number of actual utterances in the language. And so this, if you believe the kind of cognitive science view that our brain is actually processing this would kind of imply that there's a huge amount of symbol processing that's going on in our brains behind the scenes, in addition to just the actual utterances of the language. So anyway, so these grammar rules just say, well, a sentence is composed of subject, verb, object. And what do these symbols mean? Well, a subject can be some noun phrase. A noun phrase can be the word the followed by a noun. And a noun can be a person, or a noun can be a store. So in the same way a regular expression has pipe to refer to alternatives, in grammars, we can just have multiple rules for the same grammar construct. So in an English grammar, you just have noun is every possible dictionary word noun, or all the new ones that get added by you young people who are making up new words, or by writers who make up new words. This is the way alternation works. You have multiple rules for the same symbol, for the same grammar symbol. And then of course we have verb here and we have object. And as some of you already pointed out, these rules enforce a particular order on the sentences. So while the store walks to the person is syntactically valid according to these rules, the person the store walks to is not valid because there's no so it's not valid. Does everyone see that? Does anyone see why that's the case? So what I'm saying is that the store walks to the person might be perfectly meaningless, but it's also perfectly syntactically valid according to these rules, whereas the store person walks to is not valid according to these syntactic rules. Does anyone have a question why this is not syntactically valid, this sentence, according to the grammar rules that I put out here? Sure. And we're actually going to see why this is when we look a little bit more at grammars. So if a sentence has to be subject, verb, object, and our sentence says the store person walks to, well, we can kind of capture walks to. Well, we know that that's a verb. We know that the store is a noun phrase. Well, actually, I should say we know store is a noun. We know walks to is a verb. We know the noun is a noun phrase. And we know person is a noun. But now we have a set of symbols here in the order noun, phrase, noun, and verb. And there's no rule in our language grammar here that allows for noun, phrase, followed by noun, followed by verb. Does that make sense to the person who asked this? So I'm going to formalize this a little more. I mean, this is a lot easier to see. So this is actually a really good question, because this makes the formalism in the Dragon book and in parsing, I think, a lot clearer. So anyway, I pointed this out, that special symbols represent language constructs. So I don't think I have to go through this again. I think I already sort of pointed this out, that this the notion of this hierarchical syntax is one explanation, one model for why we can understand and speak these kind of sentences. So not only understand them, but speak them. So in some sense, when we're just saying the person walks to the store and somebody's like, can you just be more explicit about who that person is? You have no problem saying the person, kind of freeze that sentence for a second. The person that I went to school with walks to the store. And so you have no problem generating that kind of nested structure. And the listener has no problem understanding that nested structure and associating walking with the person. So we talked about alternatives. Okay, so let me get into the formalism a little bit. Yeah, so exactly. So somebody said the person walks isn't valid in this grammar because walks is not but that's not because of grammar. That's because walks is not part of the set of utterances in this language. I cheated a little bit by having walks to be one word in the language, but that's why. It's really because that's not a word in the language. We'd have to break that down into like verb phrases, and it's a pain to try to do this for natural language. All right, so let me formalize some of these concepts. So that those words in the language, formally these are called terminals, and we'll see why this terminology is used in a second. But these are the terminals of the language. So just remember in your head the words of the language, the actual ASCII characters in our source code, in our compiler. These are the terminals of the language. It's what Flex produces. It's what the Lexer produces. The Lexer produces the terminals of the language. So the terminals, that's for all the differences in, say, body language or written language or spoken language. That's all captured by terminal symbols. The non-terminal symbols, these are those unspoken symbols that represent the structure of the language, like sentence or noun phrase. We never have to say, the person, stop, I'm now talking about a verb phrase, or now talking about a modifier that modifies person. We never say that and then say, okay, now I'm returning to the sentence. We never utter these words, we never utter these symbols that represent the different syntactic units in the language. Those are the unspoken parts, and those are the ones that represent the structures themselves. So it's this kind of plays in nicely to this notion of cognitive science and computing, Because whereas if you think of language as being this kind of abstract thing where English just kind of exists without any physical realization, it makes it hard to, makes it hard to write a computer program that processes language. But if we think of these unspoken parts of the language as physically real, as their own symbols, then we can write a computer program that can manipulate those unspoken parts of the language in the same way that it can manipulate the spoken parts. Okay, so those are non-terminals. And I really went off the page here. Okay, those rules where we have an arrow separating some non-terminal symbol with the things that make up that grammar construct, those are called productions. And in the kind of grammars we're going to look at here, context-free grammars, we have one non-terminal followed by an arrow followed by a list of other symbols. They can be either non-terminals or terminals. In the same way, a noun phrase could be one terminal, the, followed by some other non-terminal that can expand into a bunch of other alternatives. And then we, of course, have the starting symbol. This is the top of the hierarchy. This is like sentence or paragraph or program in our Bison grammar. Okay, questions on this so far? This is just terminology. Any questions so far about grammars? Okay. So we got a couple minutes, so let's get into this. Okay. So this we can formalize this notion of seeing how a utterance in the language matches the grammar using a derivation. So this is all getting into like the formal stuff, but the same thing that I did here in showing how an utterance follows the rules of a grammar. This is captured in the notion of a derivation. So with a derivation, we start with that starting symbol, like sentence, and we just pick some production in the language, one of the rules, and then substitute the symbol, the starting symbol, with all of the symbols on the right-hand side. So for this case of the store walks to the person, we start with the sentence, and there's only one possible alternative. So we just replace it with, so usually you use, I don't know, we can use a double arrow to say this is replacing sentence with the symbols that make up that sentence. And then in each step, we take one of the non-terminals in the language and replace it with its production, with the symbols that its production says. So a subject is, what was it, a noun phrase? I'm forgetting what this is. You see that? So we've taken the subject rule. Let me actually go back to my set of rules here. So we've taken the subject rule and we've applied it to the subject symbol in our derivation, starting from the top of this grammar. And then we just keep, oh, this is going to suck. Let me do it this way. So we start with a sentence, and each step of this derivation, we just take one non-terminal and replace it with, use some rule to replace it with some symbols that start getting us closer to the utterances in the language. Is this making sense so far? Is this clear? Any questions on this so far? And if we keep doing this process, we'll eventually get to some symbol that actually has alternatives. And at this point, we have a choice. So there's two possible nouns at this point. And so the question for us is, if we're, say, generating language, the theory that Chomsky had is that these grammar rules are actually literally used when we generate languages. So in our brains, the theory goes, is that we're physically able to do this kind of grammar walking and generating a sentence from this grammar. So if we wanted to say the store walks to the person, we would pick the store alternative for this noun. And if we continue this process, this verb will only has one option to derive from. Object becomes noun phrase. Noun phrase becomes the noun, and then noun, we pick person for this. Does it make sense, this notion of a derivation? So that's all it is. It's just starting from the starting symbol, pick a rule, substitute that symbol with the symbols that it represents, that make up that grammar rule, to make up that non-terminal, that symbol that represents the grammar construct. And we just keep doing this over and over and over until we reach only terminals in the language. And this is why, I think why the terminology is used. Terminal is when the derivations stop. Non-terminals keeps the derivations going. And terminals correspond to what the actual utterances in the language is. So if we're starting from a sentence, yeah, exactly, when the derivation terminates, or at least when this process that we're using in our head to generate this language, the theoretical process, not necessarily proven, but the theory is that if we're using this process to generate a sentence in language, once we hit terminals, then we do an utterance, then we actually speak or write. And so in cases where you have the person that I went to school with walks to the store, you'd have some, that would capture this exactly, where that person I went to the store with is some choice about having some modifier on the person. And as you're generating this language and walking this tree, you make a choice to pick that kind of modifier to use, freeze the sentence, derive that part of the sentence, and then continue deriving the sentence that you froze while you were coming up with that derivation of the modifier for the person. Questions on this so far? Periods are basically the same as, yeah, in a sense, yeah. And there are some programming languages that use a period. I think COBOL, uses period to reflect the same idea of a written language, where it's like, yeah, this means an end. Now notice, in spoken language, how do you say period? I mean, some people do say period, but that's really a sentence that means extra emphasis, that like end of discussion. I'm not, that's what that means. But nobody actually says the period. So period is purely part of the written language, actually. It's not part of the spoken language. And in fact, you don't actually need, so that's why some languages don't even have a semicolon, because you can infer the end of a sentence from the grammar structure. C doesn't do that. C has a lot of help to the parser to make it easier to parse, but not all languages need this kind of help, depending on how you define the grammar. Okay, so I'm already 4 minutes over, so let's take a break. Let's reconvene at 11:30. I'll be here for several minutes to answer questions about this, and then we'll look at the inverse of this process, parsing, going from sentence to the derivation of that. And I'll be here for questions. Yeah, Python is a case that doesn't have this, although they use spacing, white space, actually, to identify nesting, which is a little weird. So somebody asks, statement list is a production, correct? Yes, exactly right. So I'll try to get to this at the end, but there's different ways. Bison has a different syntax for. So somebody's asking, so regex can parse context-free grammar. I guess you're looking at the homework already to answer this. So I have a question for you in response. Can regex parse context-free grammars? So if I have a language like HTML, can HTML be parsed with a regular expression? Can it be parsed with a grammar? So you may not know this yet, but yes, it can be parsed with a grammar. So can regular expressions parse? Well, can the languages that regular expressions represent, can they also represent languages represented by a context-free grammar? No, they can't, because if there are some languages that a grammar can represent, like stuff with matched parentheses, but a regular expression can't, then it's the case that that there are languages. So basically, there are languages that context-free grammars can represent that regular expressions can't. So regular context-free grammars can represent all languages that regular expressions can. We didn't really go over that, but that also means that regular expressions are not as powerful as context-free grammars. That regular expressions, yeah, there are languages that regular expressions can't process, but context-free grammars can. I don't know. Does that answer your question? Right. Yeah. The matching braces example is an example of that. Yeah, that's one. Well, subclassing. So somebody says context-free grammar inherits regex. So yeah, it depends on what you mean by inherits. It's a little tricky to think about subclassing or subtyping for this. Think of it more as like set inclusion. So the set of all languages that regular expressions can match is a subset of the languages that context-free grammars can represent. So yeah, I mean, subclassing, I guess, is, yeah, I think so. I think subtyping can sort of captures that also. But I had to think for a second whether that was the right way to put it. Okay, if there's no more questions, I'm going to take a little break as well, and then we'll reconvene at 11:30.
Professor, if you're talking, we can't hear you.
Hello, I'm here. Okay. Okay, welcome back, everybody. Oh yeah, sorry, I was just trying to do some. Oh, there we go. I was just trying to set up the whiteboard for later. Okay, before we, so yeah, welcome back, everybody. It's it's 11:31. So let's begin. So before we left for the break, we were talking about hierarchical syntax, how that can be represented with grammars, and we can use derivations to show how we go from a grammar to an utterance in the language. And the terminals are those spoken parts of the language, and the non-terminals are symbols that represent the structure of the language. Yeah, so somebody asked during the break, which is related to the homework question, which is, can regular expressions match those languages represented by context-free grammars? And so the answer is no. We have this matched parenthesis example. There are examples of languages where a context-free grammar can match them, but a regular expression can't. So the set of possible languages that a context-free grammar can represent is a superset of the languages that a regular expression can represent. So there's also, you can actually, because context-free grammars have alternation and they have concatenation, and you can do clean star using recursion. They're basically, you can take any regular expression and represent it using a context-free grammar. So I'm not going to go too much into that for the sake of time, but I think you'll probably do that in discrete too if you haven't taken that already. But you can leave it as an exercise to yourself to see, give yourself a regular expression and see, can you turn that into a context-free grammar and vice versa for certain context-free grammars. Not all context-free grammars can do that, but some of them are languages that can be represented with regular expressions. Okay, so we had this notion of a derivation, and a derivation takes some grammar, starting from the starting symbol, starts using the productions, the rules, to replace symbols with the components that make up that grammar construct. So sentence is replaced with subject, verb, object, and so on until we stop or terminate at the terminal symbols. And so this leads to a definition of another kind of definition of what parsing is. So parsing is the task where you take a string that you already have in your language and try to infer a derivation that goes from the starting symbol, applies rules, and generates that string in the language. So it's basically the inverse of this process of derivation. So I think one of the original theories behind this grammar is called the generative grammar, that the way language is produced in the brain is there's some structure in the brain that captures like what a grammar rule does in some finite amount of space in the brain. And by basically doing a derivation, by following these rules, you can emit any kind of utterance in the language, basically arbitrarily large sentences in the language. And if you take, like we have lists of statements in Bison, you could think of that in English language, you have lists of sentences. So you can just say on and on and on and on. You can just say sentence after sentence, and arbitrarily large and complex sentences with just a finite representation of that language in the grammar. And so in some sense, this taking a derivation is easier than parsing, because parsing is trying to infer a derivation from a sentence in the language. It's basically taking this process and trying to do it backwards, or trying to do it forwards and try to guess which production you need to take in order to reach that sentence in the language. Does this kind of make sense from this perspective? So parsing is just trying to figure out what the derivation would be for that particular string in some given set of grammar rules. And so this is important when it comes to language processing, because if we believe that languages are produced with this grammar, then the string itself has no explicit information about what that syntax is. But by knowing the grammar rules, a parser can infer that just because it knows how the sentences are generated, it can infer what the derivation was for that particular language. Now, another thing we're not going to go too much into is ambiguity in grammar, syntactic ambiguity. So there are grammars where you can have multiple derivations for the same sentence in the language. And you can read over the Dragon book to look into this, but context-free grammars can also be ambiguous in that for the same sentence in the language, there are multiple ways to create a derivation to kind of traverse that grammar to make a sentence in that language. And as you can imagine, for programming languages, because we want determinism, having ambiguity in the grammar, that at least ambiguity that we never resolve, is not really something that we want. C++, of course, does have ambiguity in the grammar, but it's resolved semantically later in the process in the compiler. So somebody asked, the lexer makes everything into tokens, and the parser goes through the tokens and calculates the derivations of those tokens. Yeah, exactly. Exactly. The lexer makes the tokens, the parser reads those and produces a derivation. And produces a derivation of that. All right, and so to really, I hope, bring this home, let's take a look at this same sentence. And instead of drawing, so I'm going to draw a derivation in a different way. So instead of using this double arrow thing, I'm going to use this format to do it. Is this looking familiar to anyone? Could anyone tell me what kind of structure this is? It's a tree, exactly. It's a tree. So this notion of derivation, where we take each rule and successively replace it using productions, can just be modeled as a tree structure that associates the left side of a production, the non-terminal symbol, with the symbols that compose it, the right-hand side. And we can capture those relationships with a tree structure. Instead of a derivation, we have a tree structure where each arrow represents one component of the right-hand side of that rule, in this case, one child. And so what do we see? Okay, so in the tree form, what can we observe about non-terminals versus terminals in terms of tree structure? Well, they're strings. Is there anything common about the terminals in the tree? Yeah, exactly, the leaves. The terminals end up as the leaves of the tree, because that's where the derivation stops. They don't have other children. Well, okay, so terminals are children, but what about, say, inner nodes, like subject? Is subject a leaf? Subject's not a leaf. Is subject a child? So subject's definitely a child. Subject's a child of sentence. So the only thing that's not a child is the root. Right, yeah, exactly. So they're inner nodes. I think this is called inner node, right? An inner node is a node in a tree that has children. and leaves are the ones that don't. So, okay, so this is exactly why we're making an AST. An AST in the parser, it's just a computer science way to take a string in the language, using a set of grammar rules, construct a derivation for that according to the grammar rules. And that gives us not only a proof that that string is a member of that language, a part of that language, part of the definition, but it also gives us a representation of that string that captures all of the grammar constructs in which the leaves are members. So these leaves are members of particular grammar constructs. Those grammar constructs are members of some other grammar constructs. And this gives us a nice representation that we can use to now do our language processing. Either maybe it's static analysis and bug finding, maybe it's metrics about the code, maybe you want to write an interpreter, or in our case, we can walk this tree and spit out the equivalent assembly code for each one of these grammar constructs by just walking the tree. All right, questions on this. So hopefully this brings together recursion, language, the computation, writing programs, and how these are all like very, very closely related, at least this presentation of linguistics. And also ties together these computational models. So remember, I was telling you that it's useful as a programmer to have these other models of computation like automata or pushdown automata to help us model problems in programming. So in this language processing problem, there's this highly recursive nature to it. And so, one way to do it is with a recursive program. One way is you could have an automata to process this kind of thing. But certainly it's the case that writing machine code, assembly code with just gotos and spaghetti code is a lot harder to reason about this problem of parsing than it is when you have a language with recursion or when you have a way to specify an automaton. So hopefully a recursion is a little bit, I hope this makes recursion a little easier, because now we can think of it in the context of language and just think of recursion as this relationship between a parent construct and its children. And traversal is just the way we can process this language. Okay, questions on this so far? What questions do you have? Okay, I hope it's clear. I hope that means everybody is sort of getting it. So there's this nice correspondence between language and computation. So let me, wow, okay. So Chomsky, another contribution he made was to define this hierarchy of language. So just like I think this is something more appropriate for big discrete. I don't know if we have much time to get into it, but as we observed in one case with matching parentheses or matching curly braces, context-free grammars, the languages they represent, which you can call context-free languages, can represent everything that a regular expression can. That is, all regular languages being those that have to be represented with a regular expression, can also be represented with a context-free grammar. And another way to say that is that all regular languages are a subset of all the context-free languages. And he defines a further two kinds of languages that have increasing expressivity. So context-sensitive languages, which we're not going to go into the grammar specification of these, but a context-sensitive language is a case like, where the syntax around a particular symbol affects which production you use. So for instance, in programming languages, depending on the type declaration of a symbol, that symbol may either be used in a function call or in a variable access. So you can't use variables as in a function call. And so that's one context-sensitive part of the C language. Now, compilers don't use context-sensitive grammars to specify that. Instead, they use a separate processing phase on the abstract syntax tree. But you could possibly use a grammar where you define rules in the productions around the left-hand side of the non-terminal to restrict those symbols declared to be functions to only use the function production for that symbol. In compilers, typically we just take the context, we use a context-free specification of the grammar, and then we use later phases to rule out invalid parts of the language. So when you get a compiler error that says parse error, that means it violated the context-free syntax of that language. Usually languages are context-free. It actually turns out that parsing C is actually not possible. You actually can't parse C in a context-free grammar. And I can show that a little bit if people are interested. And then once we have that abstract syntax tree may actually represent an invalid program. So if you have an undeclared identifier or you're using the wrong type, then the type checker is going to reject that program, even though the grammar allowed that program, said that was a valid C program according to our grammar. But we'll see that when we get into type checking a little more. And the other kind of really cool part about this is that just like a regular expression can be represented with a finite state machine, there's this correspondence between each level of this kind of language representation that Chomsky pointed out in the hierarchy. So context-free grammars can be recognized or generated with a pushdown automaton. A context-sensitive language can be represented with a linear bounded non-deterministic Turing machine. So I think this just means it has, actually, I probably shouldn't talk. I'm not too up on this theory. And then this notion of a recursively enumerable language that Chomsky pointed out can be recognized with a Turing machine. So there's this correspondence between these computational models and these language models, which is kind of a cool result. I mean, there's this, it's kind of an interesting thing that if we take this this cognitive view of language where there's these physical processes with language, it's interesting that there's this correspondence between computation. And I'll let you explore the philosophical implications of that. I don't know the answers, but I think it's an interesting correspondence. But one thing that it means from the compiler point of view is that we can define languages that no machine processes, and we can write a computer program that can actually process that language. And we can define computation in languages as well. So we can define C that does computation. Okay. And so this is the same hierarchy, but just using the computation models of computation instead. So anything that a Turing machine, anything that a finite state machine can process, a pushdown automata can also process. So if somebody has combinatorial logic, so combinational logic, actually, I don't know what combinatorial logic is. Okay, so I guess it's just Boolean logic. Yeah, I think it's just what you can do with gates, I guess. I think it's, I think it might just be equivalent to like propositional logic or Boolean logic. Is this different? Okay, I'm not exactly sure. Could read the Wikipedia page. It seems to be represented to, related to Boolean logic. Okay, so let's take a look at how these parsing algorithms actually work. So abstractly, yeah, it's a push down. You can use a push down automaton to do it. We've seen that we can use recursion to do it. And we don't, unfortunately, we don't have too much time to go into all the different flavors of parsing algorithms. There's a whole bunch of different trade-offs between efficiency and state space. And this is actually an area that I'm interested in. This is where I've did some work in graduate school. So I have a very big interest in this area, but I don't think we have much time to go into much of the details of this. So I'm just going to pick a couple of algorithms to go through, give you some homework to just work through one of these algorithms. But let's look at the kind of space of these, and also look at the Dragon Book, Chapter 4. They will go through a lot of the basics of some of the more common parsing algorithms. And parsing is largely it's a much more slow-moving field. A lot of work has been done on it, but there's still new innovations coming out, new tools that try to replace Bison. Bison has some limitations, some issues. It generates C. Maybe there's other ways to do parser generation. It doesn't generate ASTs automatically, so there's all sorts of engineering problems as well in parsing. But okay, so the first kind of parser is what we saw in the toy compiler, and it's a recursive descent parser. And so hopefully the reason for this recursion is now clear and natural for language because of this recursive structure of language. If we want to process the structure, we can use just a bunch of recursive function calls to do it. So, well, there's some question here. Was it lexers that are basically the best they can be? Can you clarify the question? Well, so lexers correspond to regular expressions. Lexers use regular expressions to match words in the input. But because regular expressions can't represent this kind of nested structure, the parser uses grammars that take the lexer's output, the tokens or the terminals, as input to the parser, and then infer this grammar structure from the parser. Oh, I mean, both are. Parsers are largely considered solved, but there's definitely still researchers who are working on it. It's just less common. I mean, lexers and parsers, if you just look in terms of, lexers, if you look in terms of regular expressions, that's pretty well solved. Yeah, actually, I shouldn't say that. There's always possible research that can be done. I guess it's just the amount of output is a lot less on regular languages and parsers versus other areas of programming languages. But yeah, it's very hard to say there's ever like no more problems left to solve in research. There's almost always something that you can look at in research. But yeah, it's definitely not dead. I mean, I shouldn't say that. I mean, I have worked in this area, but it's just much less common because there's other problems that have received less attention. Okay, so the first kind of parser that we actually already looked at is this recursive descent parser. And so simply speaking, for each non-terminal, we have one function. And inside of that function, it's basically performing the derivation. It's calling it's either matching the non-terminal with the input, or it's calling a constituent non-terminal's recursive function. So it's a fairly straightforward mapping from a grammar to a recursive descent parser. You just take each production, that's a new function. The name of the function is the name of the non-terminal on the left-hand side, and the body of the function is the right-hand side of the rule. So exactly what we saw in the toy compiler. So if you're curious about this, the Dragon Book talks about this. Go revisit the toy compiler and you can see this recursive structure happening and this mapping from the grammar to the set of recursive function calls. And they're recursive because when you have lists of things or arbitrarily nested stuff, ultimately some trace of that call stack is going to eventually call one of its parent functions. So that's why it's recursive descent. But as you saw in the derivation, in order to start from the starting symbol, there are alternative productions that we could pick to reach that string in the language. And so if we're trying to reach a particular string in the language, there are many possible alternatives that we could take to try to reach that. Some of those alternatives are wrong alternatives. So if we picked the noun that that was person instead of store, well, that wouldn't be a valid derivation of that sentence. It doesn't mean the language isn't part of that grammar, doesn't mean the sentence is not part of that language. It just means that we didn't pick the right derivation. And so one of the challenges of recursive descent is that when there are alternative productions, in which real-world grammars there are many, we have to explore every possible alternative in that grammar in order to find the right one. And so if you've ever seen dynamic programming or backtracking algorithms, you can apply that kind of algorithm to this recursive descent parsing, where you basically just explore every possibility in every possible derivation until you get to the right derivation. But researchers have made this much more efficient over time. So there's a technique called predictive parsing, which you can read about in the Dragon book, where you use the next symbol in the input to predict which production is going to be the next production in your derivation. Now, the problem is this only works in some grammars because you can't determine a single token that determines which production to take based on, for any arbitrary grammar. It only works for certain grammars. There's also dynamic programming techniques with memoization, where if you explore a path and it was the wrong path, you keep track of the result of that exploration, and you can use it to avoid recomputing stuff when you are exploring other derivations. And you can actually make linear time parsers that way. So actually my advisor in grad school did some work on this, which was originally done by this other guy, Brian Ford, who made these parsers called Rat Parsers. I don't think this is in the Dragon book, but it's a newer kind of parser where they do this kind of dynamic programming memoization to make backtracking parsers more efficient. My advisor, Robert Grimm, did some work on this to make modular syntax possible with this, so you can reuse grammars and make new languages out of existing languages. Okay, so that's recursive descent. I'm not going to cover that too much. Let me see where I am in this. Oh, okay. We actually have a good amount of time. So questions on that so far? I think I have time to kind of go into this a little more if somebody's curious about this. Let me actually show the toy compiler just to try to make this clear. So we can see the toy compiler's grammar can kind of infer it from each of these recursive functions. So this is a statement list construct, and its production maps statement list to some symbols. So it matches either the end token, that's what that if statement shows us here, and then exits, or it matches statement followed by statement list. So you see that? Does that make sense? With statement, we can see a similar kind of pattern here with the recursion, where a statement maps to an expression followed by a semicolon token. So for non-terminals, we recursively start trying to derive a string from that symbol, which recursively try to continue the derivation and expression. And for non-terminals, we just match to see if that terminal is in the input. So that's our semicolon terminal. And similarly for expression, you can see that it's just matching tokens. So it matches a number, matches an operator, matches a number, no other recursive calls here. So it's all pure terminals in this construct. Questions on that? Does that kind of make sense? And similarly, I hope this makes a little clearer what this grammar means for simple C. The syntax is a little different for Bison, but this colon is the same thing as an arrow. And the pipe is the same thing as providing multiple alternatives to the production. It's the same thing. It's just Bison has some other syntax, which is, I think, probably closer to like BNF or ENF notation. There's all these notations for doing grammar. Yeah, it's very similar to the sentence production. Exactly. So the same way, it's the same kind of meta language we use for describing a sentence grammar. We're just using it to describe our programming language grammar. And one of the kind of important parts. So okay, so look here. This is a thing that matches the open curly brace and the closed curly brace. That's what a compound statement does. You know, think when you write programming languages, or when you write C or something, you use curly braces to say, well, all of this stuff between the curly braces, that kind of goes together somehow. If it's an if statement, it goes together in that only those statements only get run if the if statement expression evaluates to true. And so this compound statement is what's capturing that nested structure here. Ah, great. I'm glad to hear somebody saying so simple. And notice that one of the symbols underneath of compound statement is statement list. So let's take a look at statement list. Statement list takes a statement to yet another statement list. So here now we have a kind of self-referential grammar rule here where a statement list can have a statement list as a child. And this is where, this is why you can have this arbitrarily large programs with just this finite description of the language. We can represent all possible simple C programs using this fairly small finite representation, but every single simple C program can be parsed and recognized by this grammar. Okay, somebody asked, how many productions does the actual grammar for C have, for regular C? That's a really good question. I had the C grammar here somewhere. Let me, well, actually, I in my research work, I have a version of the grammar that I use. I took it from this guy Roskind, who wrote up a Bison or Yak grammar for C. And this is the easiest place I can think to show it. So there's a bunch of other stuff going on here. But yeah, this guy here, James Roskind, decades ago made a grammar for standard C at the time. I had to add new productions for extensions to the language and extensions to GCC. But this is a Bison grammar. You can see it has the same kind of structure, although this generates, the parser I have is in Java, so I have to do some tricks to get the parsing tables into Java. But you can see here are all the grammar productions for C. So I don't know how many there are, but I'm on line 255 right now. And I'm just going to keep going. So there's also some semantic actions here, but mostly it's parsing. Mostly it's grammar productions. Okay, that's done. So I'm done on line 1880 or about 1888. So that's what, 1888 minus 250. So a good 1,600, 1,500, 1,600 lines of grammar for C. Now, some of this stuff you might be able to make it fewer lines. I don't know how many productions this is, but it's many dozens of productions. Well, actually, if you consider all the alternatives, it's hundreds of them. Yeah, so lots. So somebody says they like simple C better. Yeah, this is why I made it simple C. I wanted to have a language that you're familiar with, C. I mean, there's different philosophies around teaching compilers. You can either give someone a completely new language, so they don't have any kind of preconceived notions about the language that they're processing, or you can, what I did is I gave you a language you're familiar with, so that when you're processing it, you know what the semantics should be. I don't have to define formally the semantics. So you can formally define the meaning of languages. Grammars are one part of that formal specification of the language, and semantic actions are one way to define the semantic behavior of the language. So in this case, I'm just doing some capturing a little bit of the type information. So since I do have a little time, let me show you the reason that the C language is actually not, can't actually be parsed with a context-free grammar. So the grammar where you have a single non-terminal on the left and on the left of a production, the C actually can't be parsed with that. So let me show you an example of a construct in C. So I have a question for everyone. What kind of construct is this in C? Is it a function definition? Is it a declaration? Is it a statement? Is it an if statement? Is it a while loop? Which construct in C is this X star Y semicolon? Okay, so somebody says statement. Any other votes? I should have a vote for this to see what it is. So let me make this. Let me give some hints here. An expression. So it's not an expression. It has an expression in it. It's not a function. Yeah, it would be. It could be an expression without the semicolon, but I'm asking about the entire sequence of 4 tokens. So it's not, it's not an expression alone. It has an expression in it. It's not a function. So let me, instead of including this header here, let me add this line. Now, what kind of construct do you think this is? Is this still a statement? Maybe you, so not everyone is familiar with this type def syntax, but I'm curious if anybody has any other votes. So now it's a declaration. So the thing is, if we want to write a grammar that parses these sentences, we don't know whether this thing is a statement or a declaration unless we know whether X is declared as a type def or X is declared as just a variable. So it could be either of these. And in fact, using the preprocessor, you can have it be different depending on which configuration you have. Now that's not really done in practice because it's ultra confusing. But this means that we actually can't write a context-free. Yeah, exactly right. So somebody mentions that we need some sort of memory for proper nouns. That's a good way to put it. So declared symbols in the language, when the programmer declares a symbol, we actually need to keep track in some separate state, just like regular expressions versus grammars. We need some extra state to keep track of this nesting structure. To keep track of the special meaning of symbols, we need some context or some state that keeps track of those mappings. And we'll look at this next week when we talk about type checking. But when it comes to the grammar, that means that we can't write a grammar. So if we write a grammar, actually you can see this in my parser somewhere. Let's look for star here. So in my grammar, so star means several things. So star, just like unary, minus, and multiplication are the same symbol. So okay, C grammar is extremely heinous to look at. But this is the use of star as a pointer declaration. So star is before some type. The other use of star is inside of, so these are all related to pointers. So this is star used as a unary operator. So you can see it's in 2 places in the grammar. I'm sorry, I'm sorry, unary operator is the pointer dereference. And then there's the binary operator somewhere. Where's the binary operator? Oh, here, multiplicative expression. So here's where it's being used as a binary operator. And it turns out that we can write this grammar, but if we allow this multiplicative expression to have an identifier, we don't know whether that identifier represents a variable or a type name. And this grammar will be, the Bison will complain because it won't be able to generate a parser for this grammar because it's not, because there's like ambiguity about which production you need to take in order to process this grammar. So anyway, this is getting a little closer into my research work, but these days I do a lot of C processing. If people are interested in that, maybe at the end of the semester when I talk about program analysis, I can get into some of that research. But okay, and the resolution is exactly what people said. We need some extra state during parsing, and one way to resolve this is during parsing we keep track of which variables are types and which symbols are types and which symbols are variables, and we use that to basically reclassify the token to be either a typedef name or an identifier. Okay, anyway, little aside, since I think I had some time since I had some extra time. Okay, another option for parsing is table driven. And this is basically just like how finite state machines work, table-driven finite state machines, where we've got a finite state automaton. It's table, it's transition table, plus some stack to keep track of those nested parts of the structure. And this is exactly what a push-down automaton is. And so the way this works is that the production rules themselves, the individual production rules, well, we can treat that as basically like a regular language, regular expression. So for an individual production, we can use a transition table to keep track of which symbols we've matched so far in that transition table. But in order to pause that matching and go on to another non-terminal and match its production, we use the stack to keep track of which state we were in before we paused to process some other production. And so there's many variations of this table-driven approach. Just read the Dragon Book for all these variations. There's like top-down, bottom-up, LL, simple LR, look-ahead LR. And these are basically all just trade-offs in the efficiency or simplicity of writing the parser, the efficiency of the number of states that it has, the efficiency of how long it takes to do parsing, whether it's linear time parsing or superlinear parsing. And it's a trade-off in all those kinds of efficiency versus the classes of grammars it supports. So as I kind of hinted at with predictive parsing makes for efficient recursive descent, but it only works for certain grammars where you can determine some property of the grammar that allows you to predict which production that you match based on a particular token. That's not always possible for all grammars. And so all these different classes of grammars trade off this kind of efficiency with which grammars are supported. So if you try to give a grammar to a parser that doesn't support that grammar, then the parser is not going to be generated for that grammar. And so in Bison, if I didn't have you actually have to hack on the grammars, but in Bison, you'll see these shift reduce conflicts. It basically doesn't know which production applies to this part of the input. But anyway, let's okay, now I'm forgetting which. Let's go over. Oh wait, what am I doing here? Oh, sorry, I'm getting lost in my slides here. Oh, I hit the wrong ad. Okay, so the one algorithm I do want to show you and have you work through, because it's the closest to a push-down automaton. It's also the type of parser that I use in my research, and it's one of the more powerful ones that it supports. different variations of it support very large classes of grammars. Although I should say that modern compilers nowadays have moved towards recursive descent parsers because of some of the ease of writing them, the ease of doing other things during parsing, the ease of doing error reporting in the compiler. But LR parsers remain a kind of classic and efficient way to do parsing. But some of the downsides is it's tricky to write grammars for them. So let's go over LR parsing kind of from a formal point of view for a little bit. So these slides are from Charlie Hughes, another professor here at UCF. So I thank him for providing me these slides. So in short, if we look at if we think of the derivation as a tree, and if we think of parsing as constructing that tree or constructing that derivation based on the input, then there are two general schemes we can use for generating that derivation. We can either start from the starting symbol and start constructing the child nodes as we go down the tree. That's called a top-down approach. That's what a recursive descent parser does. So our toy compiler started at the top, started constructing that AST from the top. Or we can work from the actual words in the language and start matching the productions at the end of the derivation, constructing the tree from the leaves to the root of the tree. And those are like the two kind of basic classes of parsing approaches. Top-down is usually recursive descent, although there are table-driven approaches. Bottom-up is usually the table-driven approaches. So reduction is the term for the reverse of a production. So reduction is when you take some symbols and you figure out which production that those symbols fit. So reduction is that inverse of production. So if production is going top down and picking some production rule to generate that parse tree, reduction is the reverse of that. We have some symbols in the input language or some non-terminals and terminals, and we figure out which production rule that created those symbols. That's reduction. Does that make sense? Yeah, the toy compiler does top down. Okay, so there's going to be a lot of math and a lot of symbols for this. We save that for big discrete. I'll try to give you some of the intuition behind this, and then we'll go over some examples. We'll go through the algorithm and how it's constructed. And then for homework, you'll just do one exercise. I'll begin the exercise. We'll begin the exercise together, and then you'll finish it for homework. Okay. So the way it works is that we've got a stack and our parsing table, our transition table, and the stack begins as an empty stack. The money sign just means end, an end sentinel to mean the end of the stack or the end of the input. And we've got our input in the language. And the goal is to read this input one word at a time. And as we go along, the stack is going to hold elements of the derivation until we reach the starting symbol. So at any given point in the, where is this? So at any given point during the parsing, the stack is going to hold those parts of the derivation we've already figured out through reduction. And the input is going to hold the suffix that we haven't yet processed. So taken together, if you push the stack and the rest of the input together, you get one step in the derivation. So remember, the derivation is starting from the starting symbol, and then each one has some mixture of terminals and non-terminals until we get to all terminals. The parser is basically taking that in reverse, and each state of the parser, the suffix of the input plus the state stack, that is one step in that derivation, working backwards in the derivation. Does that kind of make sense, kind of abstractly? So there's this connection between the derivation and the non-terminal symbols that have yet to be reduced in the derivation, a connection between that and the pushdown automaton, because the pushdown automaton is keeping track of those things that you are freezing while you're working on other productions. And of course, recursion, because recursion is just using a stack to freeze computation while you go along. So somebody asked if simple C is doing bottom up. So we don't have to worry about parsing because Bison does it for us, but Bison is an LR parser. Bison is doing LR parsing, so it's doing bottom up parsing. But from our point of view, we just think of it as like recursion, where the semantic actions are the same stuff that goes inside of the toy compilers actions. So we don't have to think about, once we have the AST, we don't have to worry about parsing or bottom up versus top down anymore. This is really just kind of internals of how Bison works. Okay, so some terminology here. The L part means you're scanning the input from left to right. The R part means you're doing a rightmost derivation. That is, you're reducing the symbols on the, if you look at the derivation, each step of the derivation, you can either expand the symbols that are on the non-terminals on the left side of the derivation or on the right side of the derivation. Right side just means you're doing the rightmost part of that. And the look ahead is how many symbols in the input that you're looking ahead in order to make your decisions about whether to, your parsing decisions. So don't worry too much about this. Look at the Dragon book for more details on this. So these are all the varieties of doing this LR parsing. So, okay, so this is the more important part for understanding how this algorithm works. So before we go into the details of the algorithm, the data that it has and the state that it has is the table, the transition table. So this transition table takes some element in the input, just like a finite state machine. We have some, the next word in the input. We look at the action table to determine what the next state will be. But with a pushdown automaton or with LR parsing, we look not only at the current state of the machine, but we look at we have a stack of current states of the machine. So we look at the top of the stack, the current word in the input, and we look at the parsing table to figure out what we do next. And so let's look at all of the, so there's several possible things that we can do next. There's 4 different actions that we can do next. We can either shift, which is just like a finite state machine. We read that token from the input, and then we transition into a new state according to our transition table. So shift is the part of the parser that is just like a finite state machine. Reduce means that we've matched a complete production. We've determined that the current sequence of input, the current sequence of terminals and non-terminals on the stack matches some production rule in our grammar. So that's the part that a finite state machine can't do, or doesn't have the machinery to do. So shift is the classic finite state machine. We have some input, we're in a current state, and we transition to a new state. Reduce is we've matched a particular grammar rule. We've matched a production rule. And the tricky part here is that once we've matched a production rule, we've also matched a non-terminal symbol. And so we need to look at the previous production that we were in and do a state transition on that non-terminal. So the finite state machine not only has transitions on terminals and non-terminals, but it also has transitions on non-terminals as well. So you think of the production as being matched by a finite state machine, but the fact that we've matched a nested production as being handled by the stack and the reduce action. So I'll go through an example to show how this actually works in practice. And then the other possible actions are except. We've finished parsing. We've seen we've seen a complete sentence in the grammar, or error. That is, this string does not match our grammar. Okay, so let's look at an actual example of this, and I'm just gonna walk through it, and then let's just walk through an example of this. Oh wait, where's the parsing table? Sorry, 1 second. Okay. Yeah, let's look at it from just looking at the grammar here. So this syntax is, of course, a little different. Everybody has their own syntax for grammars. These are non-terminals. when you have these little capital and curly and brackets, this means production. The lowercase symbols are terminals. And the starting symbol is the non-terminal of the first production. Is everyone clear on the description of the grammar here? Does anyone have questions about this grammar? Okay, so let's look at the steps that an LR parser would take when processing this grammar. Okay, so our input string is A, B, B, C, D, E. Yeah, exactly. So to translate it into Chomsky normal form or arrows, yeah, that's exactly right. What your student said, what your fellow student said. Okay, so our input string is A, B, B, C, D, E, and we're going to try to parse this using this grammar. Okay, so we take one token ahead. We look one token ahead and say, okay, if I'm on A, and this is my current state, I'm at the beginning of my state, what transition do I make? So I haven't shown the parsing table yet, but the action that would be taken according to the parsing table for this grammar would be to shift. So when we shift, we move the state that represents I've seen an A, we move that onto the stack. So now we remember the fact that we have seen an A so far in the input. And then we move on to the next input, next token in our input. So now we look at B and we say, well, okay, what does our parser tell us to do? And our parser, so without going into the details of how the steps of the algorithm works, our parser can determine that B, sorry, I'm confusing myself here. So the parser determines that there's, wait a minute. Sorry, I feel like I have the wrong example here. Yeah. Okay, let's forget about this example because I thought this one had states, but anyway, let's do the example from homework. I wanted to do this anyway during class. So let me go to the homework. Yeah, with LR, we start from the leaves and we work our way to the top of the tree. So here I've got an LR parsing table here for this grammar. So take a second to grok that grammar while I set up my notes here. So I'll walk through an example of how the LR parser takes the I need to get my string here. Okay, questions about this particular grammar? So at the bottom here is the input that I want to parse. Here is my state stack. We always start with the starting state, 0, pushed onto the stack. That's like, yeah, that tells us, yeah, so we have some starting state that we start with. And okay, so the way the algorithm works is we look ahead one token in the input. So right now we're on C in the input, and our current state is S0. So we take a look at our parsing table, and we go to the row of the state we're currently in, and look at the column to see which input token we're currently on in our input. We're doing number 4 and 5. So 5 is show the steps of the LR parsing algorithm, and 4 is the grammar for it. So we are parsing this CCD string in our input. I'll just put the ending sentinel here as well. So this is the input that we're parsing using this algorithm. Okay, so we start in the S0, the starting state, and we start with a look ahead that is pointing at the C token. So we haven't yet consumed it, we haven't yet read it in, but we look ahead one token to determine what action we do in the parser, to determine what state transitions we undertake in the parser. So CCD is like the input program. So any .simple C file or .c file is like the input program. So CCD is just one example of this one string that this grammar, that's a valid string for this grammar. So for your homework, you're going to be doing the derivation of this string, or you're going to show the parsing steps of this string and showing the derivation of that string. Yeah. So I'm just doing an example that's just like 5, but with a different string to parse. So to step back a second, the input is the utterance in the language, or the program, the simple C program that we're processing, some string in the language that the grammar represents. And the parser is basically inferring a derivation of that string according to the grammar rules. Okay, so what we do is we take a look at the next token in the input, and we look at the top of the stack. The top of the stack tells us the current state of the parser. We go to our state table and say, well, it's just like a transition table for a finite state machine. We look at the current state we're in, and we look at the next token in the input and say, what is the action that our parsing table tells us to take? So our parser tells us to shift 2. Okay, what does this mean? So shift means consume token, transition to state. So this is saying consume the token in the input and shift to the next state. Oh, thank you. I've already made a mistake. So it should be shift 3. So this is what the shift action in the LR parser means. It means consume the token from the input and transition to the next state. Now, because we're not doing a finite state machine, because we want to capture all of the nested structure of this language, the way the state stack works is we consume that token by pushing it onto the stack and pushing the new state onto the stack. So this is like a pair of symbol and state, current state of the parser. Does this make sense so far? So shift means push both the symbol onto the stack and the new state that we transition into. Questions on that so far? Does this make sense? It's going to state 3. So transition to state 3. Transition to that state. So this means shift the token from the input and then transition to state 3. With me so far? We transitioned to 3 because our input was C. I mean, we transitioned to C because our parsing table has this action that says shift, which means read the one token from the input and transition into state 3. We transition to state 3 because our parsing table says it is. So constructing this parsing table from the grammar is itself a very, very hard problem. It's described in the Dragon book. It's what Bison does for you automatically, but just to assume that there is a method to take this grammar, and just like for finite state machines, there's a way to take a regular expression and turn it into a transition table. We have a process for turning a grammar into a transition table, a parsing transition table. If we had input B on state 0, we consume a token but don't change states. Okay, so the empty ones, it's described up here in the notes, but an empty entry means an error, means that that string is not part of the language. So all of these empty ones are implicitly error, the error action. I just didn't want to write them all in there because it's going to look very, very messy. So empty, just like in a transition table, empty is used to mean dead state or error state. Okay, so shift means we consume one token from the input, which advances the look ahead pointer to the next token. It pushes that onto the stack, that token, and pushes the state that we transition to onto the stack. Okay, clear on this? The shift operation, the shift action. So now we've got a new look ahead token, and we've got a new top of our stack. So we do the same thing. We look at our we look at our parsing table and say, well, okay, I'm in state 3. So let me go to the row for state 3 here. I see that C is the next token in my input. Good, exactly. We shift 3. So it's actually the same action. So even though the action is the same, unlike a finite state machine, just because we shift into state 3 doesn't mean we're in the same state, because now the parsing stack has a different state. So even though state 3 is the same state on top of the stack itself is a different stack. It's a different state. So for a finite state machine, all we know is that now we're still in state 3, but we lose all of that information about what came before, which prevents us from being able to do this nested structure. So at this point, this is very much like a finite state machine, where we just transition between states given inputs. The difference is we have this stack recording some part of the history of the states that we've seen. Okay, so now the input, because we've consumed C, we've shifted C, now we're on D. Okay, so I'll ask you guys, we're on D as the next token in our input, and we see that now we're in state 3. Okay, good. Reduce 4 is the next action we take. So for those of you who don't see that, we go to our transition table. We're in state 3. Wait a minute. No, that's not right. We're in state 3. Okay, I got confused by the wrong answer. So we're in state 3, shown by the top of our stack. We see D in the input. So now now the action in the table says shift 6. So this is still very much like a finite state machine, where we transition from state 3 to state 6. But again, our parsing stack keeps track of the history of states that we've seen so far. All right, we advance the input again. Now we're on the sentinel token. And we're in state 6. So here, and of course I forgot to put the reduce one. Oh man, sorry about this. This is going to be royally confusing for you because I made a mistake here. Sorry about this. So this should be reduce 4. reduce 3, reduce 2, and voila. Okay, I will update this. Okay, sorry about this. Okay, so we are, so I did a little switcheroo here. I forgot to add the reduces for this and sentinel. Okay, so we're on the end sentinel here, the money sign, and we're in state 6. We're in state 6. We're in state 6 and we're on the end sentinel. And of course of course the whiteboard is freezing now because everything has to go wrong at the same time. Okay, we're in state 6 and we're on this. I don't know. Oh yeah, shift. I don't know what you mean by plus. Somebody's asking shift isn't like a plus, it's more like an equals. I'm not sure what you mean by plus and equals. Think of it like a finite state transition, a finite state machine transition. So think of it more like concatenate. If by plus you mean concatenate, well, no, I don't know what you mean by plus. It's more like concatenate in a regular expression. So okay, so somebody pointed out that if our look ahead is the end sentinel and we're in state 6, then we go to state 6, we look at the end sentinel, and the instruction says to reduce state, reduce production 4. So this is what's a little confusing about the way parsing actions are represented. This reduce means match a production, and this 4 tells us which production to match. So this is not a state. This always confuses me as well. So keep this in mind here. This, for the reduce action, the 4 does not mean a state. The 4 means a production in our input. Okay, so I had some questions here. There are some questions here. I think they mean shift transition directly to the target state instead of just adding the number. Yeah, so this has nothing to do with adding the number. This is just like in finite state machines. The state number, it just represents the state. It's not an integer that has integer operations on it. It's just a symbol that represents which state we're in. There's no operations here besides shift and reduce here, and accept an error. Those are the operations. So somebody's asking what's go to. I think they mean shift transition directly to target. Yeah, there's no adding of states. The state numbers are just symbols that represent the state. They're not integers that have operations on them. This could have just as easily have been, alpha, beta, gamma as the symbols. Yeah, shift is move to or transition to a new state. So yeah, exactly. So when we saw state 3 and we transitioned to state 3, that's because our transition table said if you're in state 3 and you see the C token, you transition to state 3 again. It's just like if you understand the finite automata, then this aspect should make sense, where it's just a transition table transitioning between states. Okay, so somebody's asking about go to, and this is actually what comes next with reduce. Okay, so reduce is a much more complicated operation. So let me step through it. A little bit more slowly. Okay, so recall that this 4 is not the state 4. This is production 4. Let me actually this is going to get a little messy, but let me put an S here for state and a P here for production. So maybe this is a little, this is very ugly. So let's say this is P4 for production 4. And this is literally the 4th production in the list. It's just a way to identify which production we're reducing. So this is saying reduce production 4. So production 4 counting from starting at 1. So this might be a little confusing. I tried to explain it here in the directions, but this is production 1. This is production 2. This is production 3. This is production 4. So these are not integers that have operations on them. These are just symbols that count. These are like, what is it? Cardinal versus ordinal or whatever it is, using numbers in that way. So this is production 4. Okay, here's the reduce operation. So let me just we'll go through it and then I'll explain the individual steps of it. No, these are the productions from question 4. So use the following parse for the above grammar. So this is the parse table for this production. So these are the productions that were used to generate this parse table. So this is the equivalence between the language representation, like a regular expression, and the automaton that recognizes that language. So in the same way, a DFA corresponds to a regular expression, a grammar corresponds to a pushdown automaton. In this case, our parsing table. Okay, so here's the reduce action. The first thing we do in the reduce action is we look at the production that's being reduced, in this case, production 4, and we count how many symbols there are on the right-hand side. So we've matched this production. We've figured out which production we're matching. And so we're going to pop we're going to pop the same number of symbols that are on the right-hand side of the production from the stack. So the reduction says we've seen in the history of the stack, we've seen all of the symbols for this production on the stack. That's what reduce means. Reduce means we've matched a complete production. So we pop off the stack that number of, so in this case, we just pop one state off the stack. Because we now know, according to our state, that we've seen a complete production, and that complete production is stored on our stack. So we pop off however many states on the stack there are that correspond to our production. Does this make sense? No, it is related. It is related because remember, we're matching this production. We've seen, so think of the derivation in reverse. We've seen that there's a D in the input, and now we can infer that the derivation of that D was due to this production in the grammar. So it is definitely related. Yeah, exactly. We pop off D, we pop off this part of the grammar, or this part of the stack. We pop this off the stack. Because we've seen a complete production. And somebody's saying, so now the top of our stack will be S3C. Well, okay, so there's a couple questions here. So now the top of the stack is S3, exactly right. So now the top state is S3. And so somebody's asking, what would happen if D was not at the top of the stack? So that wouldn't be possible because remember, whenever we do a shift, the shift table tells us that when we see a certain token, we transition to that state. So there's no way for there to be a mismatch between these two, the value part and the state part of the stack. So think of these, it's a little, I mean, these are presented in different ways. You can think of this as two separate stacks that are moving in parallel. You can think of this as one element on the stack. So that's why I drew these together. You can think of this as one element on the stack that has both a state component and both an actual symbol in the input. So you don't strictly need to have the symbol, but for doing parsing and generating the AST, this is basically the semantic value on the stack. So we pop off this entire couplet here, this entire tuple, this double of state and value. Okay, so we can, oh man, I'm running out of time. Okay, so I didn't have as much time as I thought. Let me go through the rest of the actions here, and then I'll show you where these semantic values go and how that relates to your parser. So I'll probably go about 5-10 minutes over. So if anyone needs to leave, by all means leave. When you're doing your homework, this is all recorded, of course. So you can refer back to this to follow the steps when you're doing your homework. So if you need to leave, by all means leave. My apologies for going over regularly on this, but just so this is recorded, let me go through all this, and then it'll be clear where these symbols go in a parser. So, okay, so reduce, the first thing it does is we look at the production that is being reduced. You know, the inverse of production, the inverse of produce is reduce. We look at which production it is. In this case, it's production 4. And we pop off all of the states that correspond to the states on the right-hand side of that production. In this case, there's one symbol on the right side. So we pop off one production on the right-hand side, or from the state stack. So now that leaves us with a state, leaves us back in state 3. So effectively, we've matched a production, and now we're returning to the production that had that V inside of it. Okay, so once we're in state 3, that V value, that non-terminal V, gets pushed onto the stack. So the way reduce works is, well, okay, let me write this out in better handwriting. So the way reduce works is we find the production by its number, pop off the same number of state value pairs from the stack as symbols in the production's right-hand side, and then push the non-terminal symbol of the production before it's, find the production by its number, right? Yeah, okay, thanks. And then we push the non-terminal symbol onto the stack. And so this is where goto comes into play. So look, and then we, well, okay. So let me not do it this way. Sorry, this is more disorganized than I expected. So this is where goto comes into play. We go to state 3. Oh, why is this? Of course, the iPad has to freeze. Okay, it's back. No, it's gone again. It's back again. Okay, so we take that state that we just found on the stack, and we look it up in the symbol table, state 3. But instead of looking it up on a terminal, we look it up on the non-terminal that we just reduced. So reduced pops off, does two things. It pops off the symbols on the stack that represent the right-hand side of the production that we just are reducing. And then that non-terminal that we just reduced becomes the new symbol that we look into our symbol table to find the transition for. So we pop off S6 and its corresponding value D. That gives us the value V, that gives us the symbol V because we just reduced that production. And then the goto table uses the new state on the stack plus the new symbol to tell us what the next transition is. So somebody already got ahead of me and said, okay, state 3 for V is goto 5. Exactly right. Exactly right. So goto S3V puts us in state 5. And now we just continue as we did before. So we're in state 5 now, and our input is still the ending sentinel. So we reduce we now reduce production 3. Production 3 is this production. We pop off 2 states from the stack because there are 2 symbols on the right-hand side of production because we've finally matched the other production for V. That puts us back into state 3. We push V as the symbol onto the stack and look at state 3 and V in our symbol table. State 3 and V calls go to 5 again. So we're in state 5 and we're on the ending sentinel. And of course, I made a mistake somewhere. Damn. Yes, you do. Where is my mistake here? Oh, no. Well, wait a minute. Which production did I reduce? Go to state 5. State 5 says reduce 3. We're still in state 3, and we see V. Oh, no. This is right. This is right. Sorry. I was confused. I was getting ahead of myself. So again, we're back in state 5. Sorry, this is not wrong. This is okay. So we're back in state 5 because when we reduced this production, V equals CV, we push the value V, the symbol V, onto the stack, and we use this go-to lookup, the symbol table lookup, to tell us that we transition into state 5 again. So because we're still at the end sentinel and we're in state 5, we reduce 3 again. And this makes us go to state 5 again. So we'll reduce production 3 again. We pop off 2 states from the stack and find that we have V again. But in this case, the new state, the new top of the state stack is S0 instead of S3. So then if we look at S0 and look at the transition for V, we have a new state now. Now we go to state 4. For those of you who are still with me, does this make sense? So even though we ended up in the same state, yeah, exactly. So even though we were in the same state and we had the same transition on the same symbol, because the state stack keeps track of this history of states that we saw before, basically nested productions that we're inside of, even though we had the same transition, the state stack changed in that. So where a finite state machine without a stack has no way to have that memory of what states came before. Oh, so why did I go to state 4? Sorry, I went over that a little quickly. Maybe I got it wrong. So when we, so let me go back here. So when we were in state 5 and we saw that we had so we're in state 5, we see the end sentinel. We're in state 5, we see the end sentinel. That tells us to reduce 3. So when we reduce production 3, we pop 2 symbols off the stack. That puts us now into state 0. And it means we've also seen V. Exactly. So people, okay, good. People are getting it. So we've seen, now we see state, now we're in state 0 and we see symbol V. So that puts us into state 4 this time because our state stack, because we popped off elements from the state stack, we're eventually going to reach a state that we were in before. And so, okay, good. So what's the next thing we do? We're in state 4. It says reduce 2. Very good. I did not plan my space very well here. we reduce to production 2. So production 2 pops off a single state, replaces it with A, also puts us back into state 0. Once we're in state 0 and we see A, that tells us to go to 1, state 1. So that puts us into state 1. And finally, if we're in state 1 and we're on the end symbol, we reach an accept state or accept action, and we're done. Yeah, so okay, great. So very good question. Was the example I gave predetermined to work out, or will it work for any combo of A, B, C, D? It will work for any string that this grammar matches. It doesn't just work for one string. It works for any string that this grammar represents. So just like regular expressions, the DFA will work for any string that that regular expression represents. This is equivalent except for grammars, where we can capture this hierarchical structure in the grammar. This parsing table is generated such that it will match and recognize any string that this grammar also matches. So sorry, it took me 10 minutes over to get to this punchline, but that is the punchline of it. That if you generate this automaton to correspond to this grammar, and we know from computational theory that there is a correspondence, we can have a machine that will recognize any string that is also described by this grammar, and it will reject any string that is not described by this grammar. So hopefully those who were not able to stay will see this when they do their homework. And I gave you a little bit of a harder sequence to go through. It's slightly busy work, but it'll force you to make sure that all this works out. But hopefully this makes the connection here. And this really draws the connection between recursion, which on a von Neumann architecture or a random access machine architecture, this kind of recursion is really emulated using a stack. So random access memory, we can implement a stack in it, but it's the stack that is the key to this kind of recursion. And that's why it's useful to look at this computational model versus just, let me program this in machine code and see. Oh, the difference between goto and shift. So goto and shift both do a transition, but shift is different in that it pushes consumes a token from the input and pushes that onto the stack. Reduce and goto push the non-terminal onto the stack. So goto is the transition for non-terminals. Shift is the transition for terminals. That's the key difference here. Yeah, for your homework, you use the exact same parsing table. So all I did was give you a different string. I just went over a different string in the input. For homework, you're going to use a longer string. So goto just changes the state. Yeah, I mean, reduce and goto work together to push. I don't know which think of reduce and goto as being the transition for as being the shift kind of for non-terminals, and shift being the transition and shift for terminals. Making a stack in LaTeX. You can totally handwrite this. I handwrote it. I wouldn't expect you to do this in LaTeX. And plus, yeah, I mean, make it clear. I cross out the stack to do this. Oh wow, I'm way over in this class. So let me let's just move over to office hours. So if you have questions about this, I'll be in the gather. Some other students may be there as well. So this was just a check. What do you mean by a check? No, this is the final answer. This is the final answer. The accept action. So this, yeah, I'm gonna have to make it clear next time. But this process of actions corresponds to a derivation, and it also corresponds to an abstract syntax tree. So abstract syntax trees and derivations are just different representations of the same thing. These sequence of actions also corresponds to a derivation. I'm going to have to remind myself to talk about that next time to show that how it connects together. You can see it in one of the examples in the slides here. So this example here will actually build. This will actually build the parse tree as it does the parsing, but it's basically just inferring the derivation. Anytime you have a reduce, you have one step of the derivation being completed. The final answer is either accept or reject. You don't stop the algorithm until you have accept or error. Yeah, it's implicitly generating the AST. With the Bison, you make that explicit with semantic actions. You write semantic actions that explicitly generate the actual linkages for the AST. But implicitly, the derivation, this is finding the derivation. And the derivation, as we know, is just a representation of the syntax tree, or vice versa. Okay, I'm glad I'm glad this is clicking. I'm sorry for taking this long. I shouldn't have taken that detour. I thought I had a lot of time. I got to remember not to do that. I took a little detour into C, and that put me over. But hopefully people will watch this and that will click, because I see it's clicking for a lot of students, which is great. I'm glad you're seeing this. This is very, very, this is hard stuff to wrap your head around, to be honest. This is tricky stuff. Okay, everybody, I'm going to move to office hours. Thank you for your patience. I hope people will be able to, if they need this, we'll be able to see this recording. I'll post the recording as soon as possible. Yeah, I'm going to move over to office hours. Everyone, yeah, have a good weekend. Thanks, everybody. Take care.